defects in crystalline materials, the edge dislocation in a body-centered cubic BCC crystal, and we will visualize it at the atomic scale. Let us begin with the perfect crystal. In a BCC structure, each unit cell has atoms at the 8 corners and 1 atom at the body center. These atoms repeat periodically in all directions, forming a highly ordered lattice. If every atom sits exactly at its ideal position, the crystal is perfect. But real materials are never perfect. Their mechanical behavior is dominated by defects, and among these, dislocations are the most crucial. Now, what is a dislocation? A dislocation is a line defect, meaning the disturbance in the crystal structure is concentrated along a line. Today we focus on the edge dislocation. Imagine a perfect stack of atomic planes. Now picture inserting an extra half plane of atoms into the crystal. That inserted half plane does not extend through the whole material. It ends inside the crystal. The line where this half plane terminates is the dislocation line. This is the physical meaning of an edge dislocation. In BCC metals, the most important Burger's vector is B equals A by 2, 111. Its magnitude is by B equals K3 A bar 2. This Burger's vector direction is fundamental. It applies to edge and mixed dislocations in BCC metals, such as iron, chromium, and tungsten. The most active slip systems are 110, 111, although 112, 101, and 123, 101 systems can also operate. Now let us connect this with the atomic model. First, we generate a BCC lattice by mathematically placing atoms at corner positions and body-centered positions. This gives us a block of crystal, a perfect lattice. Next, we cut the crystal using a plane equation. This divides the lattice into 2 parts. Then, atoms on one side of this plane near a specific layer are shifted slightly upward. That shift represents the insertion of the extra half plane. This simple geometric operation reproduces the atomic structure of an edge dislocation. What happens to the surrounding atoms? Above the inserted half plane, atoms are squeezed closer together. This region experiences compressive strain. Below the slip plane, atoms are pulled slightly apart. This region experiences tensile strain. So an edge dislocation creates an asymmetric stress field in the crystal. The slip plane associated with BCC dislocations is typically a 110 type plane, and the Burger's vector lies along the 111 direction within that plane. For an edge dislocation, the Burger's vector is perpendicular to the dislocation line. This geometric relationship defines the character of the dislocation. Why is this important? Because the motion of these dislocations under applied stress is what produces plastic deformation. When a metal yields, it is not atoms sliding as whole blocks. Instead, dislocations move step by step through the lattice, allowing deformation at stresses much lower than the theoretical strength. In BCC metals, dislocations have complex cores and experience significant lattice resistance, known as Peierls stress. Their motion is strongly temperature dependent, which is why BCC metals often show a ductile to brittle transition. So, to summarize, an edge dislocation in a BCC crystal is created by an extra half plane of atoms, characterized by a Burger's vector of A2, 111, usually gliding on 110 planes. It produces compressive strain above the slip plane, tensile strain below, and its movement governs the mechanical behavior of the material.